But once you replace some of the oxide anion with other anions, such as nitrogen or fluoride anion, you can change the situation completely. So, for example, you can have new geometries, and of course, now we are dealing with the extended solids material. So, by combining these units, you can have a new type of functions. So, with this new coordination, we can have a new direction in material sciences. This is what we mainly do. Actually, about 10 years ago, about 10 years ago, I reported this oxyhydride, which is prepared by using topochemical reactions starting from this barium titanium oxide, which is of course used in laptop computers. But this is of course very stable. But maybe stability is very bad for thinking about reactions such as catalysis. But in this case, we obtain this oxyhydride material. So hydride anion is less stable than oxide anion, and which may give a very nice playground for reactions of chemistry or catalysis. We observe this very nice catalytic activity, which is the ammonia synthesis catalyst in these materials. So this is one of the highlight of the mixed-anion compounds. Okay. So maybe you are not familiar with mixed-anion compounds. So you are not familiar with this mixed-anion compound. I wrote this review article on mixed-anion compounds. Maybe you may take a look. Or maybe you may take a look at this one chapter. This is the book of inorganic chemistry, and I was in charge of the mixed-anion compounds. And also, we published a textbook written in Japanese. So now we are translating it into English, which we published from this year or maybe early next year. So coming back to this review article, I presented as a figure 1 the concept of the mixed-anion compound in terms of synthesis or properties, chemical properties. So you can see here that this G, constant G, is nothing but two-dimensionalization by using mixed-anion compounds. Okay. Then actually this is a very famous superconductors. Today's guy was Stoke, he described this BCS BEC crossover behavior by using this mixed-anion compound. Actually, zirconia are coordinated by nitrogen as well as chlorine, and this makes very nice dimension. This is highlight of the mixed-anions. Okay, today I try to keep key factors 3 folds. One is perovskite. Perovskite has a lot of materials, but this is 3-dimensional. My motivation is to make some 2-dimensional layer materials. But anyway, we use this. Otherwise, mixed-anion, as I described previously. And finally, in this talk, I try to describe some thin film, epitaxial thin film stuff, especially playing with the strain in general. So, actually, my talk will be divided into 2 parts. For both, the apparent material is strontium vanadium oxide. As I said, this is peroxide structure, and this is D1 and the cubic structure and power level 1. Maybe this is not so interesting to you. But by starting from this, we actually manipulate the composition of structures. Then we got some interesting properties, which I try to show you today. So for first one, this is oxyhydride. What I did is topochemical reactions. Okay, I use ammonia in this case. I do topochemical reaction starting from this vanadium 3 powder, and in this position we got this parameter. So this is the C-axis is highly elongated, and I found that this is described by these things, and now we found the superstructure formation along 1-1-1 direction. Okay. Something is happening structurally or compositionally. Then we found that there is the oxygen vacancy data in every 5 layers, as you can see here. So in this, originally we have a corner sharing 3-dimensional network by vanadium O6 octahedron. But after this reaction, we we found that we have a kind of alternate stacking of the double tetrahedral layer and the triple octahedral layers. So we have a two-dimensional structure by using chemical reactions. So in terms of the oxide, actually the oxygen vacancy order is ubiquitous, as you can see from this material, or maybe YBCO. Actually, YBCO is the oxygen vacancy order structure as well as the A-site order structure. So there are many physics in this oxygen vacancy order. But somehow the oxyhydride, in the case of oxyhydride, there is no example of the oxygen vacancy orders. So this is the first example of this type of structures. Then originally we did a lot of things, but to make story short, first thing we need to consider is where nitrogen is located. So originally we thought that the nitrogen should be located on the cap site, the isolated site here. Yeah. But after structure characterization change, calculations by using neutrons or X-rays and so on and so forth, we realized that the oxygen is, nitrogen is not in this cap site, but distributed in this. But anyway, we solved this crystal structure. So it's very complicated. But from physics point of view, this material is very simple. Then what happened is that maybe we should consider why this type of anion vacancy occurs. So the reason is very simple. We found actually our starting material is vanadium 4+. So exchange of an ion from oxygen to nitrogen is nothing but the oxidation reactions. So actually the final material has the formal valence of 4.2+, which means that some of the oxygen, some of the vanadium takes 5+ state. But as you can see from this material in the VO4, in the vanadium 4, actually the vanadium 5+ prefer to have a tetrahedral combination, as you can see from this one. So for niobium, in this case, octahedral combination, but vanadium 5+ want to have a tetrahedral combination. Actually, this oxidative anion-exchange reactions give rise to such a layering in this way. Okay. Then, what is happening here is very interesting. So now, in this tetrahedral layer, as I mentioned, vanadium 5+, which doesn't have the electrons. So this is electronically insulating blocks. While in this octahedral block, you have vanadium valence of 3.7. So you have a conducting state. So this is I think it reminds you of this type of the artificial thin blocks by using this different type of units. Okay, this is very famous work by Stanford group. But now we started from this simple three-dimensional structure, but similar thing can be done with these topochemical anion-exchange topochemical reactions. Okay. Then in fact, there are several experiments such as NMR measurement showing that this material is very good two-dimensional conductors. This is the reaction time. So you have this vector can be decomposed into two parts. One is showing very rapid decay, showing that this should be the conducting layer. Another one, this sharp one, has very long reaction time, meaning that this is based on the vanadium 5+ in this insulated layer. And the DFT calculation made by Ochi in Osaka University is showing that two-dimensional like cylinder type cell surfaces. Okay. Then we did some, my collaborator did several experiments down to low temperature, and we observed that some transition at 6 Kelvin. It should be explained in terms of this spin density-based transitions. This is never resistivity measurement. Right. But problem is that we started from powder sample, so characterization of the property is very difficult. The next thing we did was to try to obtain the single crystal, epitaxial thin films. Okay. So please. Then we did. But what we expected that we use this LSAT substrate, and we grow the strontium vanadium OC parent material. Then we did similar reactions using flowing ammonia gas. But my colleague came to me and said, unfortunately, he failed to obtain a single crystal. So if this is a C111 directions, so if we obtain the expected single crystals, we should have some kind of stripe like this. But this is not parallel, but it's tilted. But actually, I was so happy to see this because this is kind of changing the oxygen vacancy areas. Okay. So actually, from some analysis, we found that this is 112 directions, not 111. By using this epitaxial strain, we obtain different anion vacancy. Then this is the final crystal structure. Actually, this is next one. Yeah, actually, this is the details of crystal structure analysis, and this is similar. Actually, here isostructure is this iron-based materials. Then we continue our the synthesis, CFU synthesis, but in this case, we use the strontium titanium oxide substrate, which give tensile strength. Yes. In this case, you see that this is parallel. The oxygen vacancy is parallel, 111 directions. But periodicity, you can see from this super reflections, is not 5-fold, but 6-fold. Again, by using the strain, you are able to control the direction and the periodicity of the oxygen vacancy. Then what we have done has been summarized as follows. So when this is the biaxial strain, so this is no strain, but by using STO, which is nothing but tensile strain, we are able to change the periodicity along one direction. While we apply the compressive strain, then the 112 oxygen vacancy areas are formed. And actually this strain effect was supported by DFT calculations. I collaborated with Ben Hobson, currently Michigan University, and actually this calculation showing that the strain by applying pressure obtain superstructure, namely the oxygen vacancy achieved. Then, there are many studies actually to use the epitaxial strain, the tensile strain or compressive strain, to change the physical property as you can see here. So this is orbital order or superconductivity. This property can be tuned by changing applying the strains tensile order. But from chemistry point of view, there is, as far as I know, I don't have any examples. Maybe one example, one nice material is this one. So now this is the sort of granular structures. By changing the strain, the lattice of the substrate, you can tune the direction, but composition is exactly the same. So now we have kind of different observations based on mixed-anion chemistry. So let's move on to the next topic, which is this European vanadium EuIIH. So this is oxyhydride material. So once again, we use the strontium vanadium mostly, but this is not my study. This is a study made by Mike Hayward, the professor in Oxford University. He did this reaction about 10 years ago. What he has done is very similar, but he used the calcium hydride as a reducing agent, reactants. And in this temperature, the chemical reaction occurs, leading to this circuit, the strontium vanadium EuIIH. So replacement of the oxygen with hydrogen is reducing reaction. So as a result of the electron donation, the finite material has carried the D2 electrons per vanadium. So of course now another important thing is that the anion order. So actually hydrogen, the 1/3 of hydrogen is replaced with 1/3 of oxygen are replaced with hydrogen, but all the hydrogen are occupying the orbital state. So you have this type of trans coordinations, vanadium O4H2. So this is the coordination. So that is arranging this. So anion ordering is occurring in this material. But you may think that this is just a three-dimensional structure, just the change of the anions and three-dimensional corner shell structure are retained. However, when you consider the chemical bonding of molecular orbital configurations, you see that this is electronically two-dimensional. Once again, the crystal structure is just three-dimensional. We started from the three-dimensional perovskite. But when you look at these orbitals, you see that along c-axis, namely this is the T2G orbital. So now electrons are, this is also hydral combination, but this transconfiguration gives rise to the further splitting of the EG and T2G state. As I said, there are two electrons. So two electrons located here in this dxy and dyz orbitals. So now, concerning the bondings or maybe magnetic interactions, you have to consider this dxy or dyz orbitals, as you can see here. Then along the AD plane, the vanadium O2 plane, you see that there is pi bonding. So the bonding interactions existing in this vanadium O2 planes. In contrast, along the C direction, this T2G orbital is orthogonal with the hydrogen 1s orbital. Actually, hydrogen doesn't have a p orbital. So lack of p orbital gives rise to the kind of the two-dimensional, enhancing two-dimensional. So effectively there is no interaction. So you may call that this hydrogen 1s orbital is pi orbital. Pi symmetric orbital can be cut with this hydride leader. So now we have a two-dimensional structure starting from the perovskite material, and from some magnetic measurement and so on, we know that this material in fact has is a metal-to-insulator. Certain material is paramagnetic metal, so nothing interesting. But as a result of this reduction and this scheme, we actually have a very interesting situation where the 2D of insulating state is realized. In fact, this material stays insulator at least at room temperature, so it should be very interesting. So this is the background. So what my group has done is just starting replacing strontium with EU. So here, this is the starting material. The same as strontium ion as the vanadium O3. This is cubic perovskite structure. But by using calcium hydride reacting at similar temperature, we obtain the isostructure material EuVO2H. And the further diffraction study shows that the successful formation of this material also some impurity phases or unreacted phase exist. Okay. But structure parameter, this one, is very close to the strontium-based material, indicating that the EU should take 2+ state. The strontium 2+ and EU 2+ has very similar ionic radii. So this can be that parameter similarity support the formation of EU 2+ state. Okay. Then we prepare also the epitaxial same fields, in this case using STO. Okay. Then these XRD and stem image are showing the successful formation of this structure. But maybe epitaxial strain stabilizes this material. In this case, we didn't see any impurity cases. Okay. Anyway, we got this material, same thing as well. Then, from physics point of view, this material shows anti-ferromagnetic state together with the ferromagnetic state. As I mentioned, this vanadium has two-dimensional layer separated by a hydride ion. So actually, two-dimensional not-insulating state is also realized in this material. Actually, we did a vanadium NMR study, and we are nearly sure that this material shows anti-ferromagnetic order. The ferromagnetic order actually observed by this temperature dependence of the magnetic susceptibility. So you see that the transition temperature is something like 10 Kelvin, and the effective magnetic moment is close to 6 Bohr nanometers. Okay, this supports the ferromagnetism is responsible. EuIIH plus is responsible for ferromagnetism. But maybe you might be disappointed to see that this is just a simple ferromagnetism coming from EU and simple anti-ferromagnetic state coming from vanadium. No interactions in this powder samples. But the situation again changes when you use the epitaxial thin films. Then this is what has happened. We have actually found two important findings. One is the enhancement TC. The powder sample TC is 10 Kelvin, but when we use the thin film, the TC is enhanced. Apparently, that is parameter, when we decrease the thin film thickness, the TC enhanced. So when you make the thin film thinner, then TC enhanced. So this is one of the observations from the thin film samples. Another observation, the observation is that the magnetic anisotropy is relatively large, and also actually this is the magnetization along the easy axis, and this is magnetization along the hard axis, along the AD. So you can see that the anisotropy is very large. But when you consider the EuIIH, it doesn't carry the orbital momentum, so it's on L equals 0, so it's coming from the spin on the values. But nevertheless, we observe such a high magnetic anisotropy. And also perpendicular, considering the potential application, perpendicular magnetic anisotropy is also interesting. But anyway, we observe such a large magnetic anisotropy in these materials. Actually, this doesn't occur in the powder samples, so maybe this is another interesting features. Then the key for this unusual behavior is obtained by looking at the lattice parameter evolutions. So this is the lattice parameter, actually A-axis, B, C-axis of volume of the powder sample. But as you can see, when you decrease the thickness from here to here, the A-axis, the C-axis both reduced when decreasing the thickness. But this is unusual when you know the thinking businesses. So normally, when you apply compressive strain, the biaxial compressive strain, the C-axis, outer plane axis should be elongated. However, in the case of tensile strain, when you apply tensile strain, the C-axis, outer plane axis should be reduced. But what is happening is both axes are reduced. So A-axis, C-axis, both reduced by using this thin films, which is the steel. So this is unusual. So then we speculate that the charge transfer should occur in this material, in the thin film. So in the case of the EuIIH, the radii is something like 1.31 ohms. while the EU3 plus higher charge, so of course the radii is smaller, 1.09. So we observed that by applying the tensile strain, the was actually reduced. So maybe this EU, some of the EU becomes oxidized. So this is our speculation. But actually this speculation was supported by this X-ray absorption spectrum. So this is the spectrum depending by changing the thickness. Okay. So you see that I think this is this right-hand side show that is corresponding to the sleeper state. As you decrease the thickness, this peak intensity increases. So this means that the thinner film has more 3 plus ions. This charge transfer is okay. The charge transfer means the charge transfer from EU to vanadium. So now vanadium reduced, EU oxidized. Then we did also the high pressure. We applied high pressure. Then we did similar analysis, and we found that the vanadium, so by applying pressure, we observed the charge transfer from EU2 plus state to EU3 plus state. So now we are sure that the observing behavior is related to the charge transfer from EU to vanadium. So now two metals are interacting to give each other properties. And this one, what is this? Maybe it's also properties. So let us consider the origin, or maybe this is summarized. We summarize the origin of the intersite charge transfer in this material. So at zero ambient pressure, or maybe powder sample, as I mentioned, the EU take 2 plus, vanadium takes 3 plus 8. So at the room temperature, the vanadium insulating, auto-insulating, so there is the splitting of the XZ and YZ orbitals. So now it's half-filled state. So there are 2 electrons in these 2 orbitals. And because of the reverse interactions, that one is split based on the new values. And EU4F state should be located somewhere here. Okay. This is the embryonic state expected for this material at ambient pressure or ambient conditions. But when you apply the tensile strain, compressive strain, this XZ orbit. So now you apply the strain. So this is the dxy orbitals. So when you apply compressive strains, the interaction between these dxy orbitals should be increased. So this guy, so dxy orbital, so this is unoccupied orbital. Unoccupied orbital should be dispersed. So as you can see here, this is more or less narrow, but by applying the compressive strain or the physical pressure, you can increase or make this band width larger. Then at some point, the charge transfer. So when this level touch into this forest orbital state, so the charge transfer from the ions to vanadium. And this view is also supported from our previous report on such vanadium O2. We did the high pressure resistivity measurement, and we observed that the metal-insulator to metal transition because of the this one, dispersive empty orbital touching into the ground state, ferroenergy. Then, as you can see, melting. This band become melting. So this is the calculation, using calculations based on the GPA. when you see the dx5 orbital become significantly dispersive and finally at the pressure of 60 GPa, the spot insulating state are destabilized to change into metallic state. But in this case, before we arrive at this state, the charge transfer, so metallicity become early. So, in terms of the perpendicular magnetic anisotropy, or larger magnetic anisotropy, we may consider several scenarios, and which is not clear, but we consider these possibilities. One is the orbital hybridization between ions with strong spin-orbit interactions and those responsible for magnetism. Actually, in this symposiums, some presentation about magnetic anisotropy are shown. And for example, in this chromium I3 monolayer cases, because of the ion having very heavy, so such spin-orbit interactions should be considered. Another scenario includes spin-polarized conduction electrons, as shown in this paper, or changes in crystal field splitting based on the JJ coupling scheme. So we are not sure, but we asked Dr. Ochi of Osaka University once again, and he calculated the anisotropy perpendicular or in plane by changing this vanadium, this UD term, the vanadium interactions. Then, as you can see, when this U value is very small, the perpendicular magnetization is realized. But unfortunately, this is not quantitatively agreeing with our observation. Our observation in experiment, we observed that the anisotropy should be as large as 10 Tesla. But fortunately, this theory is only small, maybe much smaller anisotropies. So now we are not so convinced with the origin of the magnetic anisotropy or perpendicular magnetic anisotropies. But maybe this can be found with your help. So let me summarize the second part of my talk. So we obtained this new material, EuIIH, but this has an EU2 plus state and not the insulating state, but EU has shown the ferromagnetic transitions. But when you apply the strain, I mean compressive strain or pressure, external pressure, you can reduce intersite charge. So actually, in my group, we did similar strain-based things, but maybe in reality. So this is the end of the thinking works, but we made, by using mixed-anion strategy, actually we can use such a tensile or strain engineering for this type of high-pressure reactive materials. Okay. Maybe you know the high pressure is very useful for obtaining high tissue superconductivity for highly hydrogenous material, or maybe diamond is very useful, of course, for applications. But in this case, you want to stabilize some new materials at this high pressure conditions. But our strategy is different. So recently, we reported several new materials with these compositions. And this is the crystal structure, as crystal looks like. But this structure can be divided into two parts. One is this red one. This is nothing but oxide layer. And this oxide layer is sandwiched by these chalcogenide layers. And you know that maybe you know hard soft acid-base theory. So actually, this is hard layer, this is soft layer, alternatively each other. But when you apply pressure, the soft layer becomes smaller, much smaller than the oxide layer. Okay. Then what happens is that we stabilize these materials by applying pressure. ambient pressure synthesis is impossible. But somehow that pressure of 5 GPa or 10 GPa, we can get these materials. So this is maybe structure, crystal structure at 5 GPa. But of course, we have to change the temperature, we have to change the pressure. So what is happening is that here, okay? So because the chalcogenide layer has larger compressibility. So when you quench the pressure, this expands greater than the oxide layer. But we have a material, so actually this liquid O2 layer is expanded more strongly. Actually, this expansion of the liquid O2 layer is much larger than when you apply, when you prepare the same-fuse substrate. So, for example, in this material, liquid oxide, we actually realize the high-speed state in this material, not low-speed state. Actually, we can use the mixed-anion systems by using high-pressure reactions. We can manipulate the structure and interplay structures. Okay. So maybe let me summarize my talk. So we actually, this is a part of my work of mixed-anion compounds. About 6 years ago, we actually started a big national project for Japan dealing with mixed-anion compounds. We have 60 people together to work on these mixed-anion compounds. We created new materials, new synthetic technologies, new characterization technology, or maybe new properties such as catalysis. And this finished recently, but we started the international collaboration project. Currently having French guys, UK guys, Germany, Belgium. So maybe extension of such an international network is really important. If you are interested in joining us with this mixed-anion project, I am very happy. So finally, actually, our mixed-anion compound 5-year project on $10 billion project finished last year. But we are successfully extended this project. So we got now we call the ceramics. It's just an extension of the mixed-anion compounds. So now we are making different types of people. Then we can show you the property in the future. So finally, I'd like to thank my colleagues. You can see here. So yeah, this is my new website. We are just showing our photochemical reaction of mixed-anions. And this is the Kyoto University logo. But I recently met a 20-year-old young talented artist where he used color pencils. So this is the Kyoto University tree, and this is pilot. So I'm not collecting minerals, but this is I want to show the generation of the new materials. Okay. Thank you very much for your kind attention.
Thank you very much for such a very interesting and fantastic lecture. And now the lecture is open for discussion, please.
Thank you for a very nice talk. You mentioned several times charge transfer, either in rhodium or vanadium. Do you mean that you have charge fluctuations between the two valencies, or hoping of electrons between one valence to another? Those are two mechanisms.
Yeah, we have same stoichiometry in this material, of course. So we are just changing the pressure or applying strain. Then compare with the ambient pressure phase, which as you can see here, you can change the dispersions. Then charge transfer from EU to vanadium species. So vanadium valence is smaller than solvents.
Charge fluctuations between the charge fluctuation between the two valencies, or you have hoping of electron from one valence to another?
Yeah, that's a difficult question. I think in this vanadium case, I think this is metallic, so I think vanadium is itinerant. So, but in the case of EU, I'm not so sure. Maybe there is distribution of the EU2 plus EU3 plus. But this is open question. Actually, we discussed recently with my colleagues. Yeah.
Any other question, please?
This unusual strain effect, you know what I mean, when you press like this, then the plane is compressed. Could you explain it by a change in the nature of the bond in the vertical direction from ionic for oxygen to covalent for hydrogen?
So you are thinking about the
I'm thinking about the electron distribution, because in the electron distribution is covalent, it is between the atoms, and if you press, you increase the electron concentration and it attracts the proton.
We did a lot of experiments using external high pressure and changing the thickness. So I think this doesn't. And but in the previous paper on the source of vanadium EuIIH, we actually observed the partial anthracite disorder. So part of the oxide getting into the anthracite. But this is another thing, actually, what is happening that we do to chemical reactions. So you may imagine that it is so this is very, very sorry to the chemistry part. But you may imagine that maybe this optical oxygen just getting out and the hydrogen getting in. But this is not happening. Actually, in this reaction, we are not seeing, but perhaps this oxygen can also participate in this diffusion. There is kinetic issue. Kinetic issue is not discussed today. Yeah, but by carefully controlling the reaction condition, actually we can partly put oxygen into these positions.
So it is a partial substitution.
Yeah, but in this case, I'm nearly sure that this doesn't happen. But by playing with some dynamic property or kinetic property, you may manipulate the structure, composition, and so on.
Any other question or comment? I have one for you. You used NMR for some of your compounds to characterize.
NMR?
NMR, yes.
Yeah, we did NMR in this case not to show the presence of the some gluten site, but in the case of the first material, we use NMR to see the dynamic behaviors.
Is that a proton NMR or is it another?
Okay. In this study, in the first part of the talk, we use the vanadium, not proton.
Vanadium NMR.
Yeah.
Would you use proton NMRs to get even more information, or is that?
I remember we did, but information we can get from proton NMR is quite limited in this case. But we have different types of materials such as titanium-based oxyhydride for ammonia synthesis. We use NMR extensively. So depending on your purposes, structure, or maybe disordering or physical property, we use NMR or other methods. That is really difficult, but actually this makes mixed analysis compounds very challenging, but very interesting. So when we started mixed analysis project, most of our colleagues are from oxide field, and they only use laboratory X-ray diffraction machine to characterize structures. But now we need to use a lot of tools such as neutron diffractions to check the presence of nitrogen or hydrogen and so on. So NMR is definitely one of the most important tools for characterizations.
In the last question, I have another. There's any other question here?
You consider some kind of neutron diffraction in these samples precisely because you can play with the deuterium and hydrogen and you can see who is where is
Neutron.
neutron.
Yes.
And we did something very similar, and we demonstrated the Protus mechanism, not in this kind of material.
Yeah, as I said, the neutron is very important to characterize the oxyhydride material. So mostly hydrogen too light. So you cannot distinguish the oxygen vacants and hydride. Yeah, neutrons. But in EU, I think maybe you need to use the isotope. Yeah.
And also you can do the dynamics.
One of the ongoing projects in my group is to find some material with proton and hydrogen, which is very unusual. Mostly you have a proton-based oxide or hydride-based oxide. But now we are trying to get some unusual material with proton and hydrogen. So in air, or maybe in the solution, maybe H minus H plus should form hydrogen gas. But in the material, this type of coexisting state of hydrogen, also H plus and H minus is another. Maybe that can be used for catalysis.
I advise you to use neutron diffraction. We can discuss it.
Yeah, we use it, but maybe we should collaborate. Okay, thank you.
Any question or comment? If not, we have, if you want to make some tea or coffee, before that, I have to give the diploma to Professor Kageyama. But then we can continue in a few minutes with the workshop. Last session. Maybe perhaps Ali can make some comment in 5 minutes. So if you want to take coffee or tea. But first, I must give this diploma. Professor Kageyama.